The flange.
Here we go. What makes vectors parallel? Parallel vectors look like this. They could be different lengths as long as they're in parallel lines. Right? So they have the same direction, same or exactly opposite direction, right? Because wouldn't you consider this parallel to that one? Isn't that touchy? And also, if it's the same vector, we consider that parallel vectors, even if they're on the same line. If I put a vector like this, okay, or overlapping, as long as they have the same direction, don't have to have the same magnitude. So what makes vectors parallel? If vector 1 equals what? Now, if they're equal vectors, they don't have to be the same vector to be parallel. Well, yes, the opposite vector, vector 1, will be parallel to the opposite of vector 1, because that would be the same length but in exactly the opposite direction, so exactly the opposite direction would be on the same line. So, this is the vector 2, 4, no? And this is the vector 4, 8.
Proportional.
They're proportional. And how do we get proportional vectors? It's easier in component form, when you can just multiply by a scalar multiple, k times v2. That's what makes vectors parallel. And it doesn't have to be in component form. I can take 5 at an angle 30 and double the length, and that would be 10 at an angle 30. That will still be a parallel vector. When you're in component form, you distribute it over both components, the horizontal and vertical component, and that gives you those proportional sides. And that gives you the same slope then, right? Because slope was rise over the run, and we're keeping a proportional rise over the run. Now, what makes vectors perpendicular? Well, the old way was the slope of 1 times the slope of 2. Had to make that magic number. Negative 1, negative 1. They had to be negative reciprocals of each other. But how do you do that with vectors? Because we don't really have a slope on that. I suppose we could. If vector 1 equals a comma b, right? That means the slope of 1 is equal to what? B over a, right? Because you're going over a and up b. Over a and up b. So that's b, no, what did I say? B over a. Yeah, b over a, b over a. And so vector 2, if I call that c comma d, slope of 2 is equal to
D over C.
D over C. So if these are perpendicular, that means we got to come up with what?
DC equals negative.
That means the slope of 1 times the slope of 2 must equal negative 1. And the slope of 1 is b over a. The slope of 2 is d over c. And they have to make negative 1. Or BD has to equal negative AC. Right?
Yeah.
Or how about AC plus BD equals 0? Kind of a nice little jingle. AC plus BD.
AC.
As opposed to the parallel ones. What happens here? If vector 1, if we take the same thing here, vector 2 is equal to vector 1 times k, or vector 1 equals k times vector 2. And let's say we replace vector 2 with c comma d, right? You just distribute kc comma kd. So how can you detect if two vectors are parallel? We can look to see if their components are proportional. To see if two vectors are perpendicular, we can multiply the x-coordinates, multiply the y-coordinates of the vector, add them up, and if that's 0, then they're perpendicular. That's such a handy little trick that we have a special name for it called the dot product. This is the dot product, people.
Yeah, dot product.
That's it. V dot be the adding of the components, okay? And we just did the proof, right? And it gets a lot into this whole idea of rise over run, and what you look at as slope, but perpendicular slope is very different. So if I'm going over A and up B, I can't just go back A and down B for the perpendicular slope. That would actually give me a a vector in exactly the opposite direction is going to be parallel. And I can't just switch the two. I can't go over B and up A. Those are going to be reciprocal slopes. It's got to be the negative reciprocal slope. So it's like you have to go, you go over A and up B, you have to go over B and down A. And as a result, then, you get these products. Okay. That's a quick way to come up with something that's perpendicular. Okay, there's our dot product. If the dot product of two vectors equals 0, you like my dot there? That's substantial. It is not your dot of the decimal point. It is not the dot of a colon or a semicolon. It is the dot of the dot product. It's got to be a little bigger, people, okay? Not so big that it gets the size of your eyeball, but big enough that you can tell the difference between that and multiplication. Because remember, sometimes you use a dot for multiplication.
Yeah.
So that's why we like to make it substantial, okay? When if the dot product of two vectors is 0, then the two vectors are?
Perpendicular.
Spell it with me now.
P-E-R-P. Indicular.
P-E, per, pen,
Dicular.
dicular. I think that's 13 letters. Okay. And then there's our symbol from geometry, which I will accept. If you want to save some time writing out your proofs and whatnot and your explanations. Perpendicular symbol, set on P. Okay. Question.
Yes.
Is the dot product equal to the product of two vectors?
No.
Are you sure?
Maybe. Yes. Yes, we're sure. Maybe you can.
No. Well, when did we multiply vectors? We multiply them in polar form and also rectangular form in terms of their complex number counterparts, right? And what would you get? Another complex number. So I imagine that multiplication to vectors creates another vector. Whereas a dot product
He's a scalar.
creates a scalar. So this is a big, huge no.
Rainbow star powers.
No. The dot product yields a scalar, and we're not actually going to do vector multiplication. Multiplication in polar for complex numbers made sense, and it saved us a lot of time and led to Dumont's theorem, but not for this. Okay, here's just a few remarks. Another term for perpendicular is orthogonal. It's customary to call V1 parallel to V2, even if they represent the same, even if they're collinear. You might have had that distinction in geometry. You have parallel lines, and then you're supposed to say if you have the same line, we're going to still consider those vectors parallel vectors, okay? It's what k equals 1, because this could be any real number. Now the zero vector is both parallel and perpendicular to all vectors. Clever zero. Because you can multiply any vector by 0, and you get 0, 0. If you think this dot product is 0, 0 with anything, what's going to happen? AB dot 0, 0.
It's going to be AB.
It's going to be 0 plus 0 is 0. So that's how you can argue that it is parallel and perpendicular to any vector. But if I ask you for a vector parallel or perpendicular to a given vector, don't just give me the 0 vector. Usually I add to the instructions, and it's in your homework too, a non-zero vector that's parallel to something, a non-zero vector that's perpendicular. And we'll see that come up in this first problem here. U equals 3, negative 6, and V equals 4, 2, and W equals negative 12, negative 6. Okay, find the dot product. Let's practice our dot product. U dot V. So that's 3, negative 6, dot 4, 2. So that's 3 times 4 plus negative 6 times 2, 12 and negative 12, 0. Ergo,
It's perpendicular.
ergo, U is perpendicular to V because their dot product equals 0. Okay? All right? And also find V dot W. And show they're parallel. But they also want us to come up with a dot product. Now, just because the dot product isn't 0 doesn't mean it's parallel, okay? Careful with your phraseology there. With the if-then statement, you can't change it to if not A, then not B. The positive would be true. If the dot product of two vectors are 0, then they are perpendicular. If two vectors are not perpendicular, then their dot product cannot equal 0. But don't assume that if the dot product of two vectors isn't 0, then they're... Actually, you can. You can say they're not perpendicular. Because actually that's an equivalency definition. The thing is, not perpendicular doesn't mean parallel. They could be
30 degrees.
like that, okay? V dot W, 4, 2, dotted with negative 12, negative 6. And so you get negative 48 plus negative 12. Negative 60 is hardly 0.
Basically.
Now, how do you show they're parallel? You could draw them and say, oh, look, they look so parallel.
Hardly parallel. I mean, hardly perpendicular.
We can look at the slope of V. What's the slope of V? 2 over 4, right? This is the rise and the run. Rise, and the 4 is the run. So be careful with that because it's put in XY order. So 2 over 4 of a half. And the slope of W equals
1/2.
negative 6 over negative 12, which also equals a half. Therefore, the slope of M, the slope of vector V equals the slope of vector W. So V is parallel to W. But there's an easier way. Or, what was V again? 4, 2?
Yeah.
W
Negative
is negative 12, negative 6. So V, W, looks like it's negative 3 times 4, 2. Right? I factored the negative 3 out. And now W equals negative 3 times V. So therefore, W is parallel to V. You can show that one vector is a scalar multiple of the other. And because it's a negative 3, what's this tell me about the directions V and W?
They're opposite.
Exactly opposite directions. But still, that means they're parallel. Okay? It's working, John, isn't it?
It is working.
One more fix. We just had it plugged in. Okay? Properties of the dot product.
Properties of
Why is it commutative? Because
it's using multiplication and addition.
and addition, and both those are commutative. It's multiplying the x-coordinates, that's commutative. It's adding the two results, that's commutative. So our dot product's commutative. What's supposed to go in here?
What's supposed to go where?
0.
No.
Wait, anywhere.
Yeah, I need a little space for this. Let's do a little figure in time here.
Let's use it around.
Hang on. What's getting on with that? Hang on. Here. Magnitude of U times dots magnitude of U. So that's kind of like A comma B dot A comma B, right?
Yeah.
So that's A squared plus B squared. Does that sound familiar?
It's C squared.
No. What is the magnitude of U?
A squared plus B
Square root of A squared plus B squared.
So it's the magnitude of U
So
squared.
it's the magnitude of it squared. So it's the magnitude of U squared. Okay? And here, a scalar multiple of a dot product, you can multiply it into either one. Either one, because up here we said the dot product was commutative, so I could put the other one first and multiply and sneak it in there. Notice how it doesn't distribute? Don't distribute the scalar multiplication over a dot product. You do distribute this, though. U dot V does distribute over vector addition. And these two things are going to come up in our little proof in a bit. Okay? You okay with that? Okay. Yeah, a few things to fill in the notes. Did people find access to the notes okay? So if you want to print up blank notes, you can. You can set it up for the whole chapter. Should be able to have that chapter ahead of you already.
Mr. The things that, like, the stuff that you're recording right now, how do we access?
Oh, right. The last two times I didn't record because of sound. But this time I will. And that'll be the same thing as the YouTube channel.
Oh, wow.
And it'll say group 1. They'll probably do the same thing for group 4. Okay.
They're coming back.
Well, listen, Lance is going to that. Right?
He forgets.
Now you're leaving an alert here with their stats on that.
Oh, I see what you're saying.
Okay. Okay. Now, there's another cool property, and that's the cosine of theta and u dot v. And it's a tricky proof, but it's a lot of fun, and it reviews some of the things we did with law of cosines. So here's the angle between two vectors. And let's call this, doesn't really matter, we can call this vector u and this vector v. This is the tricky part though. What do you call this? It's not u plus v because they're not head to tail, head to tail. U plus something, question mark, equals v though, right? That would be vector addition. So question mark is v minus u. So this is actually vector v minus vector u. And you know, that's what we do when I give you 2 points. And I say, come up with a vector between the 2 points. You subtract them in the reverse direction. So if I want the vector from A to B, I go B minus A with the actual coordinates of the points. And you see that happening here too. And notice when you add them up, u plus v minus u will equal v. The u and negative u will cancel out. Now let's get busy with the whole law of cosines, right? What was that law of cosines again?
A squared plus b squared.
Well, do you remember the cosine theta expansion?
C squared equals A squared.
AB, 2AB cosine.
No, all squares on the top. All squares on the top, please.
A squared plus b squared minus c squared.
Right, the two things adjacent to it, the two sides containing the angle squared. So this will be vector u's magnitude squared. Because we're not going to use the whole vector, we just need the magnitude. We just need the length of that side. Plus vector v's magnitude squared. Minus the magnitude of v minus u squared. Okay. Over 2, magnitude of u, magnitude of v, not squared, because you multiply by v. Okay.
Excelsior.
Okay. Now I think there's going to be some stuff we can expand out in here. And would it help if we replaced u and v with some components? Yeah, let's call it. Let's say vector u equals a comma b, right? And vector v equals c comma d. Now the book uses x1, x2, and x1, y1. If you like subscripts, go for it. I think we got 26 letters. Let's take advantage of it. Right?
Yeah, 26.
The advantage of using subscripts is the idea of expanding to further dimensions then. You're still going to talk about the x's and y's of each, but you're going to use a different subscript. x1, y1, z1, x2, y2. Okay? So what do we get up here then? Magnitude of u squared. Well, magnitude of u is square root of a squared plus b squared.
So it's A squared plus
And you're just going to square it. Yeah, so it's going to cancel out nicely. Magnitude of v is square root of c squared plus d squared. And that's going to square out nicely. Right? Minus, now u minus v though. Okay. Remember, or v minus u. Remember, we got to go subtracting this way. C minus a squared plus d minus b. And then square it, because I'm doing the thing's magnitude, and then I'm going to square it. Now remember, there's an extra step on this one. Because first you have to subtract the two vectors and get the vector c minus a comma d minus b. And then we found the magnitude of that. All over twice. And at this point, I'm going to leave this as the magnitude of u times the magnitude of v because I just know what I'm looking for. My final formula is going to have a product of the magnitudes at the bottom, so I'm not going to change those around. Yeah.
We used to use the letters u and v instead of the magnitude of vector u and vector v.
Yeah, you can do that. I just want to be ultra clear to everybody because they might think, oh, I dropped my vector sign and he really means a vector there, and then they might think it's a dot product underneath. But yeah, I would understand that, and I would read it like that. That's why I'm very picky about those vector symbols go. But if you want to just say 2uv at this point, that's acceptable. The book gets by with it by using that bold-faced print all the time for vectors. Okay. Do you have a bold-faced printer on your pen there?
Yes.
You can work on that. No, you don't need to do it. If you leave the vector tail off, I'll assume you're talking about the magnitude of the vector. So we get a squared plus b squared plus c squared plus d squared minus, can we do this all at once here? Expand the binomial and then subtract everything. So minus c squared, and then you get your minus 2ac, but it's going to be plus 2ac, right? And then plus a squared, but it's going to be minus because we're subtracting the whole thing. Plus d squared, minus d squared, plus 2bd, minus b squared. Mongolian barbecue? No.
Mongolian grill.
That's MG.
BD is Mongolian
Oh,
grill.
BD. Oh, okay, fine. Over 2UV. And look at the magic, folks. Oh my gosh. Look at all those things that canceling.
Oh, yes.
It's raining yellow.
Oh, it makes everything straight.
Yeah, I don't know. And what's left?
It does 2AC plus 2B.
It's a product
All over
It is a maybe. Magnitude of U, magnitude of V.
You can factor out the 2 and
Factor out the 2, so you get AC plus BD all over U plus times V, the magnitude of U, magnitude of V, which is, here's the big conclusion. Oh, we need more space.
2 dot B.
Right. The cosine of theta equals U dot V over UV. Okay? Magnitude of U times the magnitude of V. Okay? Now, how can the cosine equal a vector? How can the cosine of an angle equal a vector?
It's the scalar over another scalar.
Right, because it's the dot product of two vectors gives you a scalar, just a real number, and you divide it by another real number. These are the magnitudes. Alright? So there's degree. Now find the measure of theta, the angle between vectors 1, 2, and 3, negative 3, 1. And let's do the picture over here. Over 1, up 2. There's 1. Back 3, up 1. I'm thinking that's pretty close to, well, that's going to be close to 90, but I think it's a little shy, right? So I just did a picture to get a rough idea. So the cosine of theta, the angle between, will be the dot product of the two vectors divided by the square root of 1 squared plus 2 squared, the square root of negative 3 squared plus 1 squared. Look for my mistake, people.
Yes.
Where did I err?
Make it not bigger.
Vectors poorly.
Make it not bigger.
Yeah, you need parentheses around the negative here. Thank
Make it not bigger.
Oh, yeah, that's
you. The dot is not nearly big enough, yes.
Make it as big as an eye.
As big as you fill in the dots at your standardized tests. Okay?
It's like squares now.
So I get negative 3 plus 2 over the square root of 5, square root of 10, right? So that's negative 1 over square root of 50, negative 1 over 5 root 2. Okay? So the cosine of theta equals negative 1 over 5 root 2. You want to do the inverse. Now that's a number pretty close to 1. Did we go past 90 or below 90? The cosine's negative.
It's past.
Must be a little past 90. So let's try it. Let's do the inverse cosine. Nice thing about cosine is it's going to tell us if it's going to be obtuse or acute. We don't have that ambiguity. Since the cosine's negative, it's definitely going to be obtuse. And what do you come up with, kids?
You come up with 7.
I had the answer written down here somewhere. 98.13. So 98.1 degrees is fine. Here's 10th of a degree. That's fine. Okay. All right. Think this is our last example? We're all set with that? Okay. Example 3, I think I got a picture for this one too. There's the picture. And notice you want to find the measure of angle P, which is right here. Here's P at 2, 1. And Q is at 4, 7. And R is at negative 2, 4. Find the measure of angle P, so you need to get the vectors that come together at P.
Why do you choose vectors?
Oh, because we take a dot product with vectors? Yeah, you bring up an excellent point, John. Because a lot of kids plunge into this problem, and they start taking a dot product of like these two. No. These two, 2, 1 is the point 2, comma 1.
No.
If you want to think of it as the vector, then it's from the origin, like this, and then it's not a side of the triangle anymore. So you have to look at vectors because they're going to represent the sides of the triangle. So to find the angle theta here, or P in this case, angle theta, let's call it right there.
Do we have to expect this whole problem? Just like find the spikes on the sides.
So you really want, huh? Enjoy. But if you sit there and go through the distance formula for each of these, right?
No.
And then you're still not done, because then you got to put in the law of cosines. And basically read into everything we did. I put it to you, Joy, that this is going to be less work. If we say theta equals the angle twixt the vector PQ and the vector PR. And that's not easy, that's not hard to find PQ. From P to Q is 2, 6. Do you see how I eyeball that from the change? You're going 2 in the X and you're adding another 6 on the Y. PR, you're going from 2 to -2, so that's back 4, and 1 to 4 is up 3. So PR equals -4, 3. And that bears out in our pictures here, okay? So there's PQ and there's PR. So the cosine of theta, shh. The microphone picks up all speech. I can actually count the times you're interrupting the lesson and send that to the teacher. This is the amazing power of technology. Okay? Yeah.
The D.
The D. The D. The guy that collects the D slips. Yeah. Okay. Cosine of theta is going to be 2, 6 dot -4, 3. Notice I'm not using the corners of the triangle. I'm using the vectors that represent the sides of the triangle because they give me the direction and also the magnitude. Notice if I'm trying to find this angle though, as long as I had vectors that were parallel to this, it would be fine. So I could actually pick something out here. Because we can still establish the direction, and we're trying to find an angle theta between 2 directions. So the magnitudes are relevant. But it is important here because you have to compare the dot product with the magnitudes to get the right cosine. So you get the square root of 2 squared plus 6 squared, square root of -4 squared plus 3 squared. I'm not going to fool you on that one, so we're just going to go like that. So we get the cosine of theta equals -8 and 18 all over square root of 40 5 times 5. So that's 10 over 2 square roots of 10 times 5. So that's 1 over the square root of 10. So if the cosine theta equals 1 over the square root of 10, yeah, we're pretty close to 90 because 1 over the square root of 10 is kind of small. Not that small, it's like a third. So theta equals the inverse cosine of 1 over the square root of 10. And you get something, I think this time a little less than 90 because we are definitely have a positive value. The cosine's positive and the inverse positive. 71.6 degrees. Okay? All right. Let's stop there. I'm going to put up the screen again for the homework problems if there's, because there's still a few blanks. Some people didn't get a chance to say it, right? Okay, let's get those filled in. Okay. Let's say it with me now. Flange.
Flange out.